Now, please open Google Colab. So one thing is to implement UNet, to run the code from scratch, it actually takes a little bit of time because there are a lot of steps of computation required. So if you don't want to wait, you will require run pod to make the execution faster. I'll show you how to use run pod, but first let us write the code and implement it from scratch. I have already coded it, but I'll go through the code in step by step. So let's first start with importing libraries. So first is import torch, import torch.optim as optim, then import torch vision, from torch vision import datasets, transforms. Then from torch dot utils dot data import data loader, then import matplotlib dot pyplot as plt. That's all we need. Yeah, import math also. This is all we need for now. So here for the time being, you can connect any available compute that you have. If you have Colab Pro, connect with any TPU. So DDPM from scratch. So we'll be implementing DDPM for two datasets, MNIST or Fashion MNIST. But if you think that's a toy dataset, you can implement it on any dataset. Because at the end of the day, what really matters is, are you able to train this on a meaningful time scale, right? And in the lecture, we can only show datasets that are something that fits our 1 hour window. So we'll be keeping a toy dataset, but essentially the same model will work for any kind of generation. One thing in DDPM is that it's not promptable. By default, you can't add a text-based prompt and create an image. That is why stable diffusion is later there. That paper came, I think, 2022 or something. This was in 2020. So, but here there is no prompting, but the equivalent of prompt here is randomly sampling from the Gaussian, start with a random noise image. Then device. On stable diffusion, we don't have a live lecture, but I'll be doing a break of the stable diffusion paper, like a breakdown of the stable diffusion paper. So stable diffusion is also difficult to implement with our limited compute. But of course, we can run inference. That's not an issue. All right, so this is device just to print. So one thing I will show you is here, if we print device, it will be CPU or TPU. Okay, in this case, it's CPU, but if we run it on run pod GPU, it will show as GPU. Now let's define some hyperparameters for our model. Not hyperparameters, so to say, just some variables. First is number of time steps we are performing the forward diffusion T equal to 1500. Image size of MNIST or Fashion MNIST 28 by 28. Then batch size of images, which we will pass into the data loader, which is 128. This can be different. I'm just using standard numbers. Then epochs for which we will run, let's say 20. Yes, I will also share the link to this Colab code so that you can directly take it from here. Okay, that is epochs. Then learning rate equal to 1e minus 3, something like this. And base underscore channels equal to 64. So this base channels is the base channels that we will use in the UNet architecture. This will pass as an argument. Then first is dataset. So transform equal to transforms dot compose transforms dot to tensor. And one more transformation that we will add here is transforms dot lambda where lambda x is such that, so I'll tell you why we are doing this. X plus x multiplied by 2 minus 1. So essentially what we are doing here is making the range of numbers from instead of from 0 to 1, this will now be, instead of from -1 to 1, this will be 0 to 1, right? Or I think it's vice versa. I think it's minus 1 till +1. Yeah, the range will become -1 to +1. And in general, for UNet model training stability, if the range of these numbers are from -1 to +1, it's better. By default, the range of x will be 0 to 1. So when x is 0, this will become 0 to 2 minus 1, which is -1. When x is 1, this will be 2 minus 1, which is 1. So range will become, instead of from 0 to 1, it will become -1 to +1. Then train underscore dataset equal to datasets. So here we will use the Gemini suggestion because we are going to use MNIST. Actually, let's use fashion MNIST initially. Fashion MNIST root equal to /data. That's the folder where download will happen. Train equal to true, download equal to true, transform equal to transform. So this variable is what we are passing here. So if this is now transform underscore 1, you have to pass transform underscore 1 here. Okay. And then we don't need test data set here because we are just generating. We don't want to look at the quality of generation using testing because we can just, as a human, we can see how good the image is, how good or how bad. Then train loader is equal to data loader, where we are passing the training data set. We are passing the batch size, which was defined over here. And then shuffle equal to true, just to shuffle the data set. So these are the only two lines of part of the data set, getting the data set ready. Batch size is not defined. Okay. Okay, done. So now we can define hash forward diffusion. So in forward diffusion, actually not forward diffusion, just define the parameters first for scheduling alphas and betas. So alphas is equal to, we can define alphas as 1 minus betas. So betas is equal to torch dot linspace, which will create a distribution ranging from 0 to 0.2 in steps of 1e minus 4. So 1e minus 4, comma 0.02. So 0.02 to t, where t is 1500. Then this is 1 minus betas. So now this will be, betas will go from 0 to or close to 0 till t, but here we are starting with 0.02. Alphas will go from 1 to whatever is the highest number of beta. So 1 to 1 minus beta. Till there alphas will go. Now we have to define alpha bar and beta bar. So alpha underscore bars is equal to torch dot cumulative product. So this cum prod is like cumulative product. It will produce the pi operation which we discussed. So pi is the pi from I equal to 1 to t, where inside the pi it is alpha I. So alpha 1 multiplied by alpha 2 multiplied by etc. So this is along dimension equal to 0. So this will produce the, actually this should be alphas. This will produce the alpha bars, which will look like, if you are training something alpha bars will look like this ultimately, something like this. Okay. And let's run this. Now we can implement time embedding, but I think that we can do once the forward diffusion is fully ready. So forward diffusion parameters are ready, but forward diffusion we haven't defined. So we have to define residual blocks for UNet. We have to define attention block in the middle of the, so UNet has in the middle of it an attention block inside the UNet bottleneck over this blue color block. Let me just delete the annotations. So this blue color block is the attention block. These red color blocks are residual blocks. So we just need to define it once. We don't have to define it again and again. Okay. So, and then, so attention block is for self-attention. Then we need the DDPM UNet. This UNet will consist of residual blocks, attention blocks, and rest of the items. So first, let's define the time embedding. Forward diffusion we can come after that because it's anyway an equation. Define underscore underscore or first class time embedding nn.module. I think we had imported nn somewhere. Okay, we have not imported nn, so let's do that also. Import torch dot nns nn. Define underscore underscore init. And here we are passing self. Any other arguments if we are passing, we'll figure it out. Then super for calling the parent class. And self dot dimension is equal to dimension, which is the embedding dimension for time. So we have to pass this here. So I don't think we have defined the dimension anywhere yet, but we will define it soon. Then define forward self comma t, where t is the time. So in time embedding, half of the items are embedded using cosine function, half of the items are embedded using sine function. I'm not going to go into the detail of this. This is done almost not universally, but this is done very frequently in creating embeddings, which are not necessarily learnable embeddings. Sine and cosine embeddings are already defined embeddings, whereas learnable embeddings means you will use nn.parameter. So the half of the dimension is self.dimension divided by 2. And then we say frequencies. So I'll just show you the equation. Sine and cos embedding in position embedding. So we are currently embedding time, not position, but essentially it will look something like this. A series of sines and series of cosines will define the position embedding. This was the case with the attention is all you need paper. So inside this, there is a frequency term defined by this exponent, whatever is there inside the sine. And ultimately, what it will create is a unique time embedding for every single point, unique point of time. Here, look at this. Position in time step is 100. So here time step 0, time step 1, time step 2, etc. up to time step 100 are there. And the way it works is it's a 128 dimensional position embedding. So each row, it's very small, but each row is of 128 columns. And so here you can think of this as constructing 128 dimensional vectors to represent each point of time. Like that, there are 100 times here. So time starting from 0, 10, 20, 30, 40, etc. up to 100. And each of those timestamps are being embedded using a 128 dimensional vector. And now here, each vector is unique because of the way we select the frequency for the sine and cosine function. So this is also basically constructed using these embeddings are constructed using the sine and cosine functions. Okay. Let's leave the math of sine and cosine functions at that. Torch dot exponent of negative math dot logarithm of 10,000. So 10,000 is the same parameter used in these papers. Torch dot range, a range of. So that now sine will carry half of the dimension, cosine function will carry the other half. So device equal to half comma device equal to t dot device, and divide by half minus 1. I'm sure a bracket is missing. Yeah. Then arguments equal to t none plus frequencies of none comma 1. I'm going to go a bit fast here simply because if we spend time here, UNet, we will not get time to spend on the UNet because that is a DDPM specific thing, not embedding, not the time embedding. And then we say return or output is equal to torch dot cat for concatenation. And here we are concatenating in one vector torch dot sine of arguments, comma torch dot cosine of arguments. And this should happen along dimension equal to 1. So we essentially construct for any given unique point of time, we are able to construct sine and cosine functions, and we use sine and cosine to embed the time point. So this is not a learnable time embedding. Now I have a question. If we increase the, this t equal to 1500, what if this was, I had one more zero? How do I know that there are unique embeddings possible? I can simply increase this frequency, because if I have more frequencies available, I can represent more embeddings, more of unique embeddings, and then return output. So this is the class for time embedding. I'm just running it to make sure syntax wise it's correct. Now we can code residual block, class res block of nn.module super, before super define underscore init self super dot underscore init, and we say self dot dim. This we already did. I think self dot first item in the UNet is convolution. So first we need to define convolution, and then we will have image in the size of, okay, actually this convolution we'll define separately. For residual block, ultimately what we are doing is we are going from 64 to 64. So in some residual blocks, you keep the channel dimension the same. In some residual blocks, you are doubling the channel dimension, but the spatial dimension is not changing in the residual block. And in some residual blocks, yeah, here also in this residual block also, channel dimension remains the same. Previously, it was 128. After residual block also, it is 128. In this residual block, channel dimension remains the same. And in this residual block, channel dimension actually here decreases 128 to 64. Here also it decreases from 128 to 64. Okay. So we need to define some residual blocks to take care of all of these different conditions. So self.norm1 equal to nn dot group norm. So here we are not doing batch normalization. Apparently batch normalization is unstable because the batch size is not as high as it should be. So they did something called group normalization, where 32 is the input and output is the channel dimension, which was defined using base channels, which was 64 here. So base channel is 64. That is what we are going to pass here, but I have to define that in self. So input channel, then output channel, and then time dimension, time dim. Self.norm equal to, okay, self I have to pass, yeah. And then self dot con1 is equal to nn dot con2d. This is normally done, and then input channel is whatever is the input channel dimension, output is whatever the output channel dimension, and 3 is the filter size, padding equal to 1 to ensure that the after applying convolution, your spatial dimension is not shrinking, because if padding is 0, spatial dimension will shrink. In the original UNet paper, if you look at, they did not introduce padding, and because of that, the spatial dimension was shrinking. It was a little bit weird. So UNet paper is extremely highly cited, by the way. I think it has 100,000 citations, more than that. Yeah, 128 128K citations. This is the original UNet paper. Anyways, then n self dot norm 2 is equal to nn dot group norm of 32 comma output channel. Then self dot con 2 is equal to nn dot con 2 of output channel comma output channel comma filters is equal to 3, padding is equal to 1. So this convolution operation takes you from 64 to whatever is the value of this out channel. This convolution operation does not change the number of channels. Then self dot time projection. So time projection is here. Here you can see there is a multi-layer perceptron for projecting the sine and cosine embedding time into the final dimensionality, whatever the final dimensionality is. So self dot time projection is equal to nn dot linear. So it's a linear projection from time dimension to output channel. So channel dimension itself is the output, is the embedding dimension. So whatever is the output number of channels after the convolution operation, that is the embedding dimension for both image space images as well as the time embedding. Then self dot skip equal to nn dot con 2d input underscore channel, output underscore channel, comma. This depends on a condition, right? So if input channel is not equal to output channel, then do this, else nn dot identity. So if input channel and output channel are different, that's when you introduce the skip connection. So equal to nn dot, I think the syntax is correct. We can figure it out. So if the input and output channel dimensions are different, then you need a 2D convolution to project back from input channel, whatever that was, to output channel. If the dimensions are the same, then you define the skip connection as just an identity operation. Then define forward. Self comma x h equal to self dot conv 1 of torch dot ReLU. Okay, so first what do we want to do? We first want to, let me delete this. We have X and we are first doing group normalization. So self dot norm1 of X. Now, after doing group normalization, we are passing it through activation function, which is ReLU. So then torch dot ReLU of this. And then after passing through ReLU, you are passing it through the first convolution operation. So self dot conv1 of this guy. That is the output coming from the first convolution block in the residual block. So that is H equal to this. Then we say H equal to H plus skip H plus time embedding. So self dot time, and this time embedding you can see everywhere in the figure, wherever there are residual blocks. So this is the first time embedding, second, third, fourth, fifth, sixth. So there are 6 residual blocks. Every single one of them is getting time embedding as one of the inputs. So H equal to H plus self dot time underscore projection. And of T, but then your time projection actually is just a time variable, but your images are having 4 dimensions: batch, channel, X and Y. So here you have to expand this to 4. So this comma, none, comma, none. Actually time has 2 as we have defined here, time domain and frequency. So, and then I think there is a syntax issue here, self.time project of T, because T has not been passed. H equal to, now we use this con2 and norm2. So I'll copy this and paste it here, but then this should be norm2 and this should be con2 of not X, this should be of H, because this H we are passing here. And then you just return H plus skip connection. So self dot skip of X. So the skip connection you can see in the original paper. So this is the skip connection and it is applied in after the residual block where the channel dimension is different. So the channel dimension now has gone from 128 to 64. Actually, channel dimension has not gone down here. Okay, let me just make sure that this number is correct or not. You upsample, so number of spatial dimension increases, channel dimension does not change. And then residual up block, which means spatial dimension in general here has increased from 14 to 28, but channel dimension should eventually get back to 64. And then I think there might be a typo in this block or this block. I have to just confirm. Okay, channel dimension goes from 128 to 64, and then you will concatenate another 64 dimension to make it back into 128. And then you again make it from 128 to 64. Let me just double check if this is correct or not. I think it is correct, but I'm having a bit of confusion because then this should be 64. Yeah, okay. Here channel dimension is 64. Okay, I think it makes sense. So here, what is happening is here the channel dimension is 64. So there are skip connections in UNet, just like ResNet, and the concatenation is done along the which dimension? Along the channel dimension. And concatenation is not done for those res block whose output is not 64. So if output is not 64, so here output is 128, there is no concatenation. Here output is 128, there is no concatenation. Here output is 128, there is no concatenation. Then similarly, here the output is 64. Here And right after that, there is concatenation. And here there is 128. But I'm not 100% sure if there is one skip connection going to this one also. Like something like this, something going from here to here. I'm not 100% sure if this skip connection exists or not. Okay. So that I have to clarify. But if that skip connection was there, then this 64 would have become 64 plus 64 to 128 again. So maybe that skip connection is not there. Maybe skip connection is there only in this one. Okay, so my confusion is, guys, where all are there skip connections? Is it only at this place where the channel dimension is 64 in the output? Or is it also there here? Because here also output channel dimension is 64. But if skip connection was there here, your total channel will become 64 plus 64 right after the concatenation, which is 128. But then that is disagreeing with this, because here the input is 64 and output is 1. So here, if input is 64 here, output should be 64 here. If output has to stay as 64 here, you should not have a skip connection. So that is my logic. So I don't think there is any skip connection here, but I might be wrong. I'm 99% sure, but I'm not 100% sure. The link, collab link, I'll share right now. That's the link. Okay, so this is the rest block, and this is commonly used as rest block for all the, for the entire UNet architecture. Now we can write attention block, attention block, and then dot module, define init and self comma, maybe one more thing we might need. We'll find it out. Super dot init and first self dot norm. So this normalization is done very commonly, but here it is group norm, and group normalization such that input is 32, output is whatever is the number of channels. Then self dot, now we have to define query key value, self dot key, because this is self attention of one sequence to itself, self dot v. So the code for all these three will be the same, because you are projecting through bunch of learnable parameters. So nn dot params, actually self dot q equal to nn dot conv 2d, because you are using a 2D convolution to convert your images, because you have two-dimensional spatial information plus channels, and you have to flatten it all into one single sequence, and that sequence you are converting into query, that sequence you are converting into key and value. So nn.con 2d from channel to channel, but then the convolution filter size will not be 3, it will be just 1. So a 1D filter. And same 2D convolution we can use to convert. So a 1D convolution is used to convert the query key value, convert your input image-like features into query key value sequences. And following this, we should have a projection, self.projection equal to nn.conv 2d of channel, comma, 1. This is also fine. Then define forward, self, comma, x, then batch, comma, channel, comma, height, comma, width equal to x dot shape. Then h is equal to self dot norm of x. So this is where we use this normalization. Then q equal to self dot q of h, and but we have to do a reshaping, but I'll do that after I write this. And k equal to self dot q k of h, and values is also the same, v equal to self dot k of h. But then we have to reshape it such that we get back the image size after applying self attention. So batch comma C comma height and width is the total number of tokens in the sequence. So one mistake in what I said is we are not getting back the image size yet, because unless we unpack this dimension, we are not getting it back. We are just getting the sequence of tokens over different batches and channels. And attention equal to torch dot softmax of query dot key transpose divided by square root of d multiplied by v. So q dot transpose of key, but in transpose we are transposing not through batch dimension, it's through sequence dimension, sequence and the channel dimension. Channel dimension is same as the embedding dimension. So C is the embedding dimension basically. 1, 2 multiplied by K, or at K, divided by, we should do square root of dimensionality, embedding dimensionality, which is math.sqrt of embedding dimension is this C itself. So that is query dot key transpose softmax of that, but we do this along dimension equal to -1. So this is attention weights, but we have to multiply with value to get context vectors. So output equal to, or we can just call it as H equal to attention multiplied by V dot transpose along 1, 2, and this whole thing we can transpose back 1, 2 dot reshape such that batch, channel, height, and width we get back. So after the attention, we have to still pass it through the residual block. So inside this attention, images are considered as token sequences, but outside, just before and just after, we have to get the image back, which is why we are reshaping it back into batch, channel, height, width. And then return x plus self dot projection of h. So this is finally the, so basically you are adding context to your input. Self dot k I did instead of, oh yeah, thank you. Now let's implement the UNet. Now that we have implemented the ResNet and the attention block, this part should not take too much time. So class DDPM UNet nn.module. Then define, this part is common, so super, we don't have to pass anything. Self.UNet, we don't need. This is all Gemini suggestion, I'm just deleting it. Time dimension is equal to base underscore channels multiplied by 4. So base channels was defined as 64 outside this, which is why we don't have to pass it here. Then self dot time MLP. So time MLP is used for this projection. So self dot time MLP is equal to nn dot sequential of nn dot linear. So we need a linear projection from what dimensions? From, okay, first of all, before all of this, we have a time embedding. So time embedding, which is the class that we have defined over here. So time embedding into which we are passing the time itself. So we have the embedding vector, time embedding of number of channels. So we have base channels. So this is the vector. So originally it was base channel, which we are projecting into 4x dimension, and then we are projecting it down. We are not projecting it down, I think, from the architecture. Yeah, I think we are not projecting it down. I'm not 100% sure if there is this one was made in Figma by me. I'm not 100% sure of this B comma 256. After this, there is because 64 is projected to 256 and projected 256 is projected back into 64. I am not 100% sure. I have to check that. So because of that reason, code may have mistake. Let's see. If it runs, then it's good. Then following that activation nn.relu. Then in this linear, we have to mention the projection. So projection is from base channels to time dimension. So I don't think there is a projection back, but let's see. Then after relu, nn dot linear from, I think the way I should write this is, this part is confusing. So basically what's happening is from 64 dimensions, we are projecting to 256 dimensions. And then usually what happens is we project it back to 64 dimensions. But here in the paper, the way they implemented, as far as I understand, is 256 is put back into 256. So you are not projecting it back. You are keeping it in the same dimension. But in multi-layer perceptron, since this is the hidden layer, this is the output layer, you have to add one more nn.linear from 256, 256. So that is what we are adding now. So nn.linear from time dimension, time dimension. So that is the self.time MLP. Then self.convolution in, this is the first convolution which you see here. This one, it should match with the convolution number of filters. You mean over here, right? This one, right? And filter, if it is 64, this 256 should match this one, right? Yeah, we'll come to that. Self.con in is equal to nn.con2d. And you're going from 1 channels to number of base channels. Initially, it was grayscale, so 1 to 64. And then using 3x3 filter and with padding equal to 1. And then self, now we are defining downsampling part. Okay, so here it is downsampling. Then here it is bottleneck of the UNet. And after that, it is the upsampling. So down, up, and bottleneck. Those are the 3 parts of the UNet architecture. So self.down1 is equal to, first it's so in UNet architecture, you have rest block followed by average pooling. Okay. So self.rest block of, not self dot actually, just rest block, because rest block is defined as a class. We cannot write it as self dot this class. So we are instantiating the rest block, which these parameters, with these parameters, base underscore channels, comma. So base channel, how many output channel that block has, and the time dimension. So base channels, comma, time underscore dimension. But then output channel was same as base channel, I think, after the first rest block. Yeah, output channel was not changing. So that was also 64. Base channels, time dimension. Now the question which Kamal has asked, if this time dimension is equal to 256, how does it go well with the rest block? So in rest block, let's see how is it handled. So in the rest block, the only thing which we are doing is we are using this time projector where, so this is how it is handled, Kamal. So in the residual block, we are using one projection for time where there is, so this time dimension is 256 and we are projecting it to whatever the output dimension should be. If this particular residual block is such that output dimension is 64, time is projected back from 256 to 64. Okay, so this line of code takes care of that. Okay, so this is self down 1, and then self dot down 2 is equal to same thing. It is also a residual block, but let's see here the number of channels in the output is doubling. So here I can just say 2 times base channels in the output. That's the only difference, or base channels multiplied by 2. And then following that, there is a pooling operation that we can just say self dot pool. So this pooling operation reduces channels or spatial dimension. What does it reduce? It reduces the number of, it reduces the spatial dimension, not the channels. Average pool 2D of 2. So this will shrink the spatial dimension by half. Then we can come to the bottleneck part. Bottleneck had 2 ResNets residual blocks and 1 self attention in the middle. So self dot the middle bottleneck part 1 is equal to something, then self dot attention is equal to the attention, then self dot second block in middle 2, which is equal to something. Then here also it should be rest block, but rest block such that number of channels are input and output are 128, which is double the number of channels. So here all of it should be base channels multiplied by 2. So this should be base channels multiplied by 2. This should be base channels multiplied by 2. And same thing should repeat here also. And in attention, we already have a class here, which is called attention block. So for self dot attention, it is equal to attention block of, we have to pass base underscore channels multiplied by 2. Why is that? Because in the attention block, the number of channels that it's handling is same as whatever is there in this rest block. So if this rest block is handling number of channels multiplied by 2, which is 128, 64 multiplied by 2, which is 128, that is what we should pass to attention block channel wise. And then the upsampling. In the first part of upsampling, there is an upsampling operation. So self dot up equal to this. But then there are two residual upsampling blocks, so that we can call as self dot up 1 and self dot up 2. So these are the 3 blocks, but concatenation is there in between, but we don't need a block for it. We can simply do that in the forward pass. So we are having a self dot up for this, self dot up 1 for this, self dot up 2 for this. For concatenation, we just implement it in the forward pass. No need to define it like this. So nn dot upsample, say scaling factor is equal to 2, because you are scaling the spatial dimension by a factor of 2, scaling up, not scaling down. And mode equal to, there are few different modes. One is called bilinear interpolation, but here we are using a mode called nearest. Nearest meaning if we are creating new pixels, the new pixel value will be based on the values of the nearest, geometrically nearest pixel. Then this should be rest block as well, but rest block in such a way that input is 128, output is 64. So which means this should be base channel multiplied by 2, but here multiplied by 2 is not needed. And the last rest block will be similar to this rest block. Multiplied by 2 factor, I think it is needed. In the last rest block, you are going from 128 to 64. Yeah. So which means this should be multiplied by 2. Second one is just base channel. So this is the rest block in the up convolution. And then finally, last thing is this convolution, which takes the number of channels. Spatial dimension remains the same. Number of channels goes from 64 to 1. So self dot convolution out, con underscore out, is equal to nn dot con 2d. And we go from base number of channels to number of channels equal to 1. And that's it. Padding to make sure that the spatial dimension is not shrinking. So padding equal to 1. And convolution filter size is equal to 3. So that's it. These are the major parts that we have to define in the UNet. Then define forward, self comma x comma t. Then t is equal to, so time embedding, self dot time MLP of t. So time MLP we have defined here. Then I think this was a skip connection to be added from this output. So whatever this output is, we need to preserve that value because that has to be added as a skip connection. Okay. So I'm storing it in a variable called x. Then I will say h equal to self dot. Now it is the down arm of the unit. So down 1 of x. Then I can say, so this is d1 and d2 will be the down 2 output. So d2 is equal to self dot down 2 of d1. But one thing I forgot to do here is I have to also pass the time. So for all the rest blocks, we have to pass the time input. So down 1 and down 2 will have time input. Actually, there are 6 rest blocks, 2 rest blocks in each of the in the left arm, in the bottleneck, and in the right arm. Then h equal to self dot pool. This is to reduce the spatial dimension of whatever is this output. This is d2. Now we are in the bottleneck of the unit. So self dot mid 1 of h comma t because we are passing the time. H equal to self dot attention of h. For attention, there is no need to pass the time. And h equal to self dot mid 2 of h comma t. That is the middle part, and then the upsampling part. H equal to self dot up of h. Then we say h equal to self dot up 1 of h. This is the second rest block. First rest block in the upscaling part. Then now we have to do concatenation. So now this is where I said for concatenation, we can just do it in forward pass. This concatenation of whatever is the output coming from this, which we had stored in the variable called x. So now we have to do the concatenation. So h equal to torch dot cat of h comma d1. Actually output, not x. Output is what we have to store. So d1 is what we have to pass here because this d1 is the input that is required in the concatenation. Comma dim equal to 1. Then h equal to, now we are implementing, now UNet is entirely done except for this part, except for this 2D convolution. So h equal to self dot up 2 of h comma t. Okay, now not that. After concatenation, one residual block was missing. After residual block, the upscaling. So h equal to self dot conv, I think this was called con out of h, and then we simply return h. So that is the UNet architecture. There is a lot of lines, but logically it's not that difficult once you understand the UNet architecture. And that's it. Model equal to DDPM UNet dot to device, and optimizer equal to optim dot adamw of model dot parameters, comma learning rate equal to, we had used some variable up here, LR, equal to this. And so run this. Okay, there is some error. Model equal to DDPM UNet con 2D init missing one positional argument. Okay, and that is in the skip. Okay. So I am missing an argument in the skip, in this one. So nn dot con 2D input channel, output channel, number of kernels and padding, right? So just one. So this is the skip connection added such that if the channel input is not equal to channel output, then you have one. So you're going from input channel to output channel. I am a bit confused about the syntax here, whether it should be 3,1 or, because here the only functionality is to define whether there is this skip or not. I'm not sure if you need a 3x3 filter with learnable parameters for this. I think it should be just something like this, where filter size is like 1 by 1. Let me go with this line of code first. If it's not working, we'll see this. Okay, and just run all. Okay, DDPM UNet has no, okay, this should be parameters. Okay, now it's running. Now we are at the last stage now. I think now it's just the training loop and DDPM sampling, because see, sampling happens after training the UNet. Okay, so now it's just the training. So for epoch, this is where we discuss the loss function. So now I think you will enjoy, because the difficult part is done. So for epoch in range of epochs, for x comma dash in train underscore loader, x equal to x dot 2 of device, and time equal to torch dot rand int. And we pick so during training of the UNet, what are we doing? We are sampling a random time point between 0 and 1500. We calculate the error added, and we train the UNet to predict what that error is, right? Not the error, the epsilon value. So t equal to torch dot rand int of 0 comma t, where t, the value of t is 1500 according to us. And then we have to do x dot shape of 0 comma. So this is to get this random integer in the shape that is required for us. so that device equal to device, so that when we calculate, when we pass this, it will not cause dimensionality issue. And then now we predict the noise. This is where DDPM is coming. Okay, so noise predicted is equal to DDPM UNet of xt comma t, right? So x comma t. Then loss is equal to, it's the difference between predicted noise and actual loss squared, and you can take a mean for different data points. So noise is equal to loss, loss is equal to noise predicted minus actual noise. Actual noise is what? I don't think we have defined it here. We had to first do forward diffusion. So noise, let me look at the forward diffusion. We haven't written the forward diffusion yet, right? Underscore diffusion. I don't think we have written the forward diffusion. It's missing. Basically, this should be this something minus actual noise, predicted minus actual noise raised to 2 dot mean. Something like this. But I don't think we discussed about writing it, but we should have written it here. This can be just a function actually, forward diffusion. And noise is equal to, noise is sampled from our normal distribution, which is similar to the x naught, which has to be passed here along with the time step. So in forward diffusion, x naught comma t, then square root of square root of a bar, or a with a dash on the top, is equal to torch dot sqrt of alpha bars, which is this, of t, or of t, and this is just a number, but we need to expand it to 4 dimensions. It has, because image has batch comma channel comma width comma height, then square root of 1 minus ab, or a bar, alpha bar, is equal to torch dot sqrt of 1 minus alpha bars of t. And this also you convert such that you add batch comma, yeah, t is time steps, correct? Because in forward diffusion, we are saying starting from image x0, find the diffused or noisy image at time t. Then xt, this formula you know, sqrt underscore alpha bar multiplied by x0. This is the scaled original image multiplied with the factor, multiplied by this guy with the sampled noise, with noise. And we just need to return 2 things. Return the new image and also the noise, this noise, because this noise we'll have to compare with our predicted noise by the UNet. So this is the forward diffusion function, and copy that function's name and paste it here to predict the noise. So forward diffusion of x0 comma t should give us access to xt comma noise. So this is how it should be. And then we just use this loss in the optimizer. Optimizer dot each batch should start with fresh gradient. So dot zero grad, then loss dot backward for back propagation, and optimizer dot step, and then print epoch number. We need the epoch number. So epoch number is epoch plus 1 out of epochs. And the loss is loss dot item. To DDPM, should we pass X or XT? So, okay, that is a great question. So first of all, let me just put all of this under the for loop. Yeah, it should be XT because DDPM is trying to predict noise based on XT. Thank you so much. And but then I should define it properly. Okay, let me do this. X equal to X dot device. So this is the actual X from the data loader, and T is the time, which is we are saying, okay, create a noisy image at any random time. So to forward diffusion, we pass X and T to get XT and noise. This is also correct. And then the predicted noise from the UNet is based on model. It should be model actually. Model of xt comma t. That is also correct. Loss is, so please note this. We cannot directly use it. We have to use this model variable. Then loss is equal to predicted noise minus actual noise the whole square. I think rest of the things are fine. I don't see any mistake. And loss is equal to loss dot item to 4 decimal points dot 4f. Okay, so now if we run this, what's going to happen is this will be very slow, but I'll show you how slow it is. Then I will show you how to run this on run pod. Okay, for x comma in train loader. Okay, noise predicted equal to model of xt comma t. Positional argument t is missing. Let me check if. Okay, yeah. So here it should be self comma. Is it t or time dimension? Not dimension. Time dimension is out defined, I think, here itself. Base channels are defined outside. Rest block dot forward is missing. Okay. Inside the model, I think there is a time missing in one of these rest blocks. Can you help me identify where is that? Time dimension. In attention. In attention, we are only expecting the channel dimension, but I'll share the original code with you. Just try it. If you can figure out where the issue is, that will be great. So this is the original code, which works because I have run it. So while you figure out the issue, I want to show you something, how to set this up to run on run code. Okay, in self.up, okay, let's see. Self.up scaling factor. In upscaling, no, time dimension we are passing only into residual blocks, right? I don't think we are passing time dimension to up blocks. Let me check in my up one. In up one, uh, oh yeah. Thank you so much. Yes. So it was missing in this line in self.up one. Okay, thank you. I think that's the issue. Let's run and see. Yeah, it's running for sure, but it takes time. So now let's see how runpod handles this. So in runpod, you can just set up an account. Of course, you have to recharge for some money. I have put some $100 and something because we use runpod for many projects. But I have one pod dedicated for. So creating a pod is easy. You create an account on runpod, add your credit card or recharge for a certain amount. Even less than $5 is enough, and then go to pods, click plus deploy, and then from all these available GPUs, pick whichever is appropriate for your particular problem statement. It's completely dependent on data set and what type of training or fine tuning are you going to do. I think for this one, I chose RTX 5090 or something else. Let me check. So this one is RTX 5090, which is costing me. So this 0.9 per hour is idling time, which is the store. They give us some storage space. So there is some expense associated with utilizing their storage. But if you are running, there will be extra expense. So what I think you should do is create a pod, run your code, then download everything which you need, which you got from the code. Once that is ready, just delete the or terminate it like this. So stop pod so that you won't incur any expense. So the way this works is you click, or once you click deploy, you will see something like this, where a Jupyter Lab hyperlink will show up to open Jupyter Lab. And if you click this, Jupyter Lab will be opened, but this Jupyter Lab will be opening on RunPod's server. Okay. So whatever files are there will be there on RunPod server. So what I have done is whatever I wrote in Colab, I just downloaded as an IPy notebook and I just uploaded like this as an IPNB, and then that code is what you see here. And then here actually running execution is much faster. The slower part was data download in my opinion, but let me just first run the code and I'll just show you the generated images. So these are the generated images from Fashion MNIST. I think I can just directly run this once. Yeah, see, so I trained instead of MNIST, I trained for Fashion MNIST, and each time now our DDPM sampling is generating image from a pure noise image. So you can see that these images, if you remember, the variational autoencoder lecture, this is much better image than variational autoencoder because there such features inside the t-shirt was not coming. How do you select a specific GPU? So what I look for is mainly the cost. Okay, if I have time to wait, I don't care about the running speed. So if you look at the pods here, some of them are $4.99 per hour. So this I will not choose. This I will not choose. I don't need it. But the good thing is these GPUs are also faster. So your code may execute fast. So actually, there is a lot of science that goes behind figuring out what GPU works the best for you if you really want to do cost optimization. For running toy codes, I really don't care too much about cost optimization. I just go with a relatively cheap GPU, which is featured here for general purpose use. But if we are doing fine tuning, so currently we are training a 200 million parameter model from scratch for on a Hindi data set. So that we plan to release that model in public. But then when I'm doing that, I want to really cost optimize. So at that time, we are considering a lot of factors. Actually, Dr. Raj is soon releasing a playlist on GPU programming itself, not GPU programming per se, but how to think about what GPU is doing for you to cost optimize, and how can you do it yourself. But I don't have a great, unless it's a specific data set that I know what it is, like a data set from Hugging Face which you want to train on. And if a paper which use that data set is mentioning they used A100 GPU, 8 GPU hours or 40 GPU hours or whatever, that will give me an idea. Okay, this is the expected total runtime. And if I use this GPU, how much cost difference I can find. That can be calculated. But other than that, for toy datasets, I have no idea how to pick from this. I simply pick from the featured section, whichever is relatively cheap, I pick that. But then if you pick a very cheap one, I think the speed of execution will also be slow. So I don't know, the final cost will depend on your per minute or per hour cost multiplied by the minutes or hours for which you are training. So to answer your question, I don't have a great answer unless I know the specific data set. Anyways, yeah, how do you do it with custom data set? Do I need to upload it to runpod? Exactly. So currently we are also training a ResNet 50 model on runpod on one of the custom data sets. So that custom data set, we had to upload it here, because runpod also gives you storage space. It's not just like a RAM. So you can upload it and then you can, but that uploading step will be a bit slow depending on your bandwidth. Now here, I'll just show you the speed of this execution just once. Let's run this. And this time I'll run for MNIST. Actually, MNIST images are not extremely good, but they're okay. Let me just show you. So here, data download was a bit slow yesterday when I tried for the first time, but the epochs were fast. Yeah, one more thing. See here, now it's using GPU. So using device CUDA, which one is preferred, Collab Pro or runpod? Collab Pro has a lot of limitations. RAM is limited. Then keeping the collab alive is a pain, because at the end of the day, if you close it, it's gone, right? But runpod has no such issue because it's running on, unless you terminate it, it'll be running. So runpod is of course much better. No, hands down, this is the better. It's easy also because you can use just like Jupyter Lab, you can run it. Only thing is, expense wise, I'm not 100% sure how does collab and runpod compare. Yeah, see, already 3 epochs are done. 3 out of 20. But here on this one, how many epochs are done? Not even a single epoch is done. So I just ran the code on GPU. It's already wrapping up. So Azure ML Studio or runpod, I have no idea. I don't know how to look at it cost wise. I will ask ChatGPT. I don't have an answer right now. But I hope you can see how fast at least the epochs are. I'll do one thing. Let me just run for, instead of 20 epochs, just run for 5 epochs and let's see. So 5 and train. So what I suggest you do is, I'm not sure if runpod gives do they give any free credit? Because it's been a long time. I'm not sure if they give free credits or not, but if they do, or if there is any way for you to get runpod free credits, try running this code. Try downloading this as an IPy notebook, IPNB, and then upload it on runpod and try running this just to see how speed-wise, how amazing or different it is when you have a proper GPU setup versus when you don't have. I mean, I don't have to say it, you all know it, but still when you experience it, it's a different feeling. So just try it once. So I'll just run these 5 epochs and then I'll show you for MNIST dataset how good the images are. In fact, in my experience, it is not as good as variational autoencoder. I thought variational autoencoder with a good latent space dimension was giving better quality images um, than this, but I'm not sure, right? I don't know. Maybe I have not run it for enough time steps. Here, 1500 is not enough, maybe. But whatever, in general, I asked this to Rajat also, who recently had same experience. So Rajat also mentioned that getting extremely good quality image on DDPM was difficult. Okay, almost wrapping up. Okay, so this is done. Now let's run DDPM sampling function and generate samples. Okay, these are the samples now for MNIST 8, 9, 4. So not good, right? Not that good. Auto VAE was much better. So time step, the one way to know if your time step is good enough or not is run the forward diffusion, okay, and plot the image to see if the image looks like a completely noisy one or if you can still make out meaning from the image. If you can still, if the image still looks like, something like this, you know that the number of time steps are not enough. So you can figure it out by trial and error. For some type of images, t equal to 250 is enough. Here I'm running for 1500, which is more than enough, I think. But whatever it is, my accuracy, my MNIST images are not the best, I would say. Still, we'll see what can be done to figure out what can be done to make DDPM much better. So I think this is a good time to stop. The lecture has been super long. I really wanted to stop by 12:30, but I think we ended up having a lot of discussions. So please try this. Please try RunPod once. One last thing which I want to mention is, let me open the course portal once. Just give me a second. Okay, so this is a link which I had shared, I think 1 or 2 days back. This is on a platform called Senja. You can leave your, if you like this course, you can leave what you liked and like a testimonial on Senja. If you are submitting a video testimonial, which we'll not be sharing without asking you, it will be, you will get a coupon code for all the courses which is mentioned on courses.visuara.ai. If you go to this link, there are a bunch of amazing courses. You will get a discount access. But otherwise, it has been an extreme pleasure of mine to teach this course. I think it has taken 17 or 18 weeks total. I planned 14 weeks, and in between there were breaks for 1 or 2 weeks. So I originally wanted to wrap up this course by beginning of January, but now we are at the end of January. 2 topics which I said I will release in a self-paced mode. One is stable diffusion and one is Dino, mostly V1. So that will be done in the next few weeks. I'll let you know through a notification. But we have come a long way, right? So right now we are at generative image generation through use with the help of transformer architecture. Although here transformer is doing very little, it's mostly done through sampling process itself. But in the previous models that we discussed in this course, it was very different. So overall, I'm sure a lot of things you remember, but a lot of things you have also forgotten. If somebody suddenly asks how the Swin transformer architecture works, maybe you'll have to sit and think for a little bit. But that is all right. Overall, I hope the major takeaway from this is how transformer architecture can be utilized for image-based data set, not just for text-based data. That is the first and foremost biggest takeaway. Second thing is, if you are building, transformer-based architecture for applications like vision language action, vision language planning, somebody was discussing in the Discord also about vision, language, action, and planning. I do plan to conduct an entire program based on VLA for autonomous driving. So how to make use of vision, language, action for self-driving cars, and this time some hardware also will be involved, like using a toy car, Raspberry Pi based, for programming it with a either a multi-model model or um, a text encoder plus a separate image encoder in Fusion. So that's my next plan for as far as vision with transformers is concerned. So I think we can wrap up the lecture here now. Please submit your thoughts on Senja, the link I have shared in the chat. So thank you so much, and I'll meet you again in one of the upcoming courses. If you have questions or if you want some advice on what all things you could be doing in the future, you can just drop an email, over here, sridath@visuara.com. Just drop an email. I may be late to reply, but I will, because the inbox is almost always crowded, but I'll try to get back to you as much as I can. So thank you so much. Please revise the material if you need, and reach out to me for technical or career-wise questions. I'll be happy to help you. Thank you so much. It was a pleasure teaching all of you. Please submit something on Senja. I'll be really happy to see your comments. So see you soon sometime later, and looking forward to seeing most of you in VLA for autonomous driving also. We'll meet hopefully soon. Bye.